Hello and welcome back to the course on artificial intelligence. In today's section, we're going to tackle deep convolutional Q-learning. So we're taking deep Q-learning to even a further step. So we originally started with Q-learning, the simple Q-learning. Then we took that to deep Q-learning, and now we're taking it to deep convolutional Q-learning. So let's see what we're going to discuss in terms of intuition. The intuition section is going to be quite quick. There's not much that we need to add as long as we're familiar with convolutional neural networks, and we'll touch on this towards the end of today's tutorial. So today in this section, we're going to talk about deep convolutional Q-learning, the intuition behind things, and why it's so powerful, why exactly it's so important to move away from deep Q-learning, and why deep Q-learning is just a basic building block, where it's just a step for us on the path to deep convolutional Q-learning, and what kind of avenues deep convolutional Q-learning opens up to, what kind of avenues the knowledge opens up to, and where it can be applied. We'll have some examples of that. And then we'll talk about eligibility trace or end-step Q-learning, a very powerful addition to the whole concept of deep Q-learning, and we'll talk about the intuition behind that. It's quite a complex topic, but nevertheless, we'll break down the intuition in quite simple terms, and then I'll give you some additional references where you can read up about eligibility trace if you'd like to go into more detail. But it is important for us to get the intuition down pat, because we're going to be using that in the practical tutorials, because we're delving into much more complex topics now that we need to add these extra elements to our agents or to our Q-learning algorithms, so that they can actually handle these complex environments and navigate them successfully. And of course, in this section, because we're talking about convolutional neural networks, it is highly advisable that you check out Annex number 2, Convolutional Neural Networks. Once again, if you've done the deep learning A to Z course, then you're already familiar with this information, so you can safely proceed with these tutorials on the deep convolutional Q-learning. If you haven't done the deep learning A to Z course, then it's a great idea to look at convolutional neural networks and look at those intuition tutorials there, so you understand better how images are processed by neural networks in order to look for features, and what's the whole convolutional layers are about, the pooling layers, the flattening layers, and how all of that works in order to come up with some parameters about that describe the environment, or that describe that image. And therefore, we're going to be using those as inputs into our neural network instead of that vector which we're talking about. But more on that in the next tutorial. So if you haven't seen those tutorials yet, we highly advise you to check them out to get up to speed with, or refresh your knowledge on convolutional neural networks. All in all, we've got an exciting section, and as you can see, quite not that many intuition tutorials, meaning that you can you'll be able to jump into the practical side of things very quickly. So on that note, I can't wait to see you in the first tutorial, and until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're starting off this section on deep convolutional Q-learning. So let's have a look at what it's all about. Previously, we talked about deep Q-learning. So we had an environment with an agent, and we had a vector describing that environment, which was fed into a neural network, and at the end, we got the Q values as our outputs. And then, of course, we found out how the network is trained, the learning part. We found out how actions are decided based on those Q values. That's an action part. And we talked about the action selection policies and different things about how deep Q learning works. But here, the key concept for all of this is, how do we get from the actual environment and the states, to the neural network? Well, the transition is over here, the input vector. So the input layer of our neural network, and it is a vector. So what we're looking at is, okay, so we're actually not the correct, it's not the correct term. We're not looking at anything. The agent basically has this information. So the environment is passing it this information, saying, okay, you, the agent, you're currently in your state is described by this vector. In this simplified example, it's described by this vector x1 of 1, x2 of 2. So your coordinates are 1, 2, and that is your whole state. In a more complex environment, the state might involve other things that the agent can be observing. But the point here is that it is paused as a vector. And the thing is that that doesn't happen in real life. In real life, yeah, except for GPS systems and other things like that, but in real life, what do we use most of the time? We use our senses. We use our eyes. Even in GPS, it's not built into our brain. It's not telling us the coordinates through our brain. And so we're still using our eyes to look at the GPS and understand what's going on there. And so this is kind of cheating for AI to be able to get like information about the environment as a vector. It's too simple. It's not how it works in real life. That's not how we as humans operate. And ultimately, we want to create artificial intelligence which can operate in a similar fashion to humans, which is as can take on the same challenges as humans. And so in the human world, we don't have that. We don't have these coordinates or other types of vectors that are passed to us that explain the state we're in that environment. So we're going to have to remove that to make it more realistic. And then what can we replace it with? What do we see, or what do we do as a human to get information? Well, most of the time we see. Of course, we use all of our senses, but most of the information that we're getting about the world around us comes through our sight. And that is why we're going to change that little arrow which we had into a whole convolutional neural network. So this is from our annex number 2. We've got the convolution layer, and that's why it's important to be quite comfortable with convolutional neural networks and how they work. So if you've done our deep learning course, then you should be comfortable with that, or you can just have a look at the annex number 2. We've got some very good intuition tutorials there. So here we've got the convolution operation which happens. So we're actually going to be looking at this as an image. So this is an image of net environment, and so the agent is actually looking at the environment. So in this case, not that he's like looking from within there, he's like looking, like let's say he's playing this on a computer and he can see this environment, and therefore he can see like where this figure representing the agent is actually is. So you can see this whole environment, or whatever a human would see. If it's actual maze, then the human would see the maze from inside, and so the agent should be able to see exactly the same thing. So whatever he sees is goes through a convolution layer, then goes through a pooling layer, goes through flattening. Again, you can find out more about these different parts of the convolutional neural network in the annex. And then after it's flattened, then we have inputs which go into the neural network. And this is way more realistic because the agent has to use their sight, or has to process images which the environment is supplying to the agent, just as a human would be processing images. And the beauty of this is not just that it's more realistic and it's kind of like more as the agent's actually more as a human would be, but it allows us to process much more complex environments. For instance, this is how we can play Doom or other games like that, because instead of just getting a vector of information, which somebody would have created for us in this environment, we can just hook up our artificial intelligence to any environment, which as humans, we would have vision of this environment. So we, as a human, when you're playing this game, you can see exactly this picture. And that's exactly what the artificial neural network or the agent would see now. So in this part of the course, when you're going to be programming the practical tutorials, the agent will actually see this exact picture. It will see the pixels. It will get this exact picture of all of the pixels, with this person, with this gun, with this face, with this percentage, with everything. Exactly what we see here, that's exactly what the agent will see. Then it will have to dissect that through convolutional layer, pooling layer, flattening, and then it will go into a neural network. And needless to say that the neural network will actually be much more complex than that. So let's replace it with something like this. This is not much more complex. This is looks a little bit more complex, but in reality, the neural networks you're going to be working with and creating with Adlan are going to be quite interesting. They're going to be much more complex than this. But as you can see already here, even if we just have 5 inputs instead of 2, things become much more complex. And here you can see we have many more actions that the agent can take. So in the game of Doom, turn left, turn right, look down, look up, run, shoot, reload, or all those different actions that are possible in a first-person shooter like Doom. And moreover, it doesn't have to be that. You can attach this agent to another type of game. That's the beauty of it, that it then realizes that it can now operate any kind of environment that you attach it to, because as long as there's like a visual representation of that environment, it's already got the whole infrastructure, the whole structure is ready to process that. So that's what deep convolutional Q-learning is all about. So we're taking it even to the next step. We're adding convolutions into, or the convolutional layers into our agent's brain now. And we're making it even more complex, and therefore we're rewarded with being able to solve even more complex challenges. So I hope you're very excited about this. This is going to be an epic section, and we're going to create some amazing things. And I can't wait to see you on the next tutorial. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're going to cover off quite a complex tutorial called eligibility trace, or n-step Q-learning. And this is something that we're going to implement in the practical side of things, so that's why we need to cover it off. And at the same time, it is quite a complex topic, so I've got a very interesting approach to getting us up to speed with the intuition behind it. So I have like a different approach in mind than we're used to. So let's have a look at that and see how that goes. So I'm going to give you an example to start off with. Like, I'm going to give you an example in this tutorial, and that will demonstrate the power of eligibility trace, and it'll give us the intuition behind things. And then if you like to delve further into eligibility trace, I'll give you the best place where you can read about it. I'll give you a reference to a book. But otherwise, so why this is going to be different is because we're going to first look, rather than delving into the intuition, we're going to look at an example, and the intuition will become obvious after we talk about it. And that's my hopes for this tutorial. So let's have a look. Let's see if we can do this. So here we've got two agents, and they're navigating the same environment. And we're going to see how these two agents work. The first one is going to work without eligibility trace. Second one is going to work with eligibility trace. And hopefully we'll see why the second one is going to be so much more powerful than the first one. So let's have a look. We're going to look at this agent first. And the way he operates is the exact way that we've discussed deep Q-learning so far. So the agent is going to take a step, or is going to take an action, move into a new state. It's going to get a certain reward. It's going to put that reward through its algorithm, update the neural network that's running this agent, or that's running in the mind of this agent. So that's basically how it's learning from the environment. Then it's going to take a new step. So from this new state, it's going to take a new action based on what its neural network is telling it to do. It's going to get a reward, it's going to update, and so on. And it's going to keep doing that. So obviously this agent is going to do quite a good job. And as we've seen previously from the previous practical tutorials, we're going to get some quite good results here. But now we're going to add a new feature. Now this agent number 2, this guy over here, he's going to navigate the same environment, but he's going to use eligibility trace. And this is what it means. What he's going to do is he's going to take n steps. He's going to take, in this case, 4 steps. He's going to take 4 steps. And then only after taking these steps will he calculate the total reward that he got from those steps, and he will put it through his network. He will put it through his neural network that's governing the decision-making process, and then the neural network will learn from that. So which one, right away, like which one do you think is more powerful? The guy that is just taking one step at a time and kind of like poking in the blind or in the dark, and he's like, okay, so I'm going to take a step, see what happens. I'm going to take a step, see what happens. I'm going to take a step, see what happens. The guy at the top. Or the guy that takes, just very courageously marches through 4 steps in a row, and then he decides whether those were good steps or not altogether. And why you can see here, or why you're probably getting a sense for why the second guy is better or is more powerful, is because the second guy actually knows what's at the end. The first guy, when he is assessing whether this step is good or not, he's only looking at the reward that he's getting. And so he's only guided by the reward the environment is giving him. Same thing here. He's only guided by the reward that this environment is giving him here. So every time, that's his only kind of compass that he has, the reward, the reward, the reward. Whereas here, he actually can assess, after taking all these steps, he can assess, oh, okay, so I did get to the finish line. So this combination of steps was good. All of them were good. Or, oh no, I ended up in the fire pit. Or, oh no, I didn't win my car didn't get to the finish line, or I crossed the sand wall, or I lost the game of Doom, or something like that. And then he decides for himself that this whole combination of steps is bad. And therefore, for these steps that are earlier on, he has more information, he has more insights. Like in a very intuitive approach. This is a much more complex topic than we're portraying here, but in an intuitive way. For example, if we take this step only has information to update it. You only have information coming back from this reward here. And for this step, in this case, the same exact step, it has more information. It has information coming all the way from, okay, so what was the outcome after 4 steps or 5 steps or whatever? Yeah, so that is how it works. And why it's called eligibility trace is because during this process, not only does he look at the cumulative reward of this of what's going on, and then the cumulative loss, and then all of that is propagated through the network, but actually there's a trace of eligibility. That's why it's called eligibility trace. There's a trace that is kept in the algorithm, which says, okay, so if we do get let's say we get a punishment, we get a negative reward, then which of these steps is most likely to be eligible for that punishment? So not only do we know what overall this whole pattern or this combination of steps is, but we also keep a trace of eligibility. Which steps are we going to update if we get a reward? So for instance, if it's a negative reward, we might have an eligibility trace that indicates to us that this is the step that is most responsible for what we got in the end. Or if it's a positive reward, again, we might know the algorithm helps us keep track. This eligibility trace algorithm helps us keep track of what step or what action is eligible to be updated based on that reward that we get. And that's why it's called eligibility trace. And so that's the basic intuition behind eligibility trace. And hopefully these two examples of these two agents make it quite obvious or quite intuitive in why eligibility trace can be so powerful. And if, as promised, if you'd like to delve further into the topic of eligibility traces or n-step Q-learning, then a wonderful, amazing book which you can find is called Reinforcement Learning: An Introduction, is by Richard Sutton and Andrew Bartow, 1998. I think they're in the process of creating a second edition, or they've already created a second edition, but this is the most common or the most popular or the most referenced book on reinforcement learning. It's got a ridiculous number of citations, I think like tens of thousands if I'm not mistaken. And also the chapter you need for this is chapter 7. So in order to look at eligibility traces, there's a whole chapter about it, chapter 7. You can read about it, and it goes into lots of detail, forward, backward eligibility traces, and also how you've got temporal difference on one hand, and on the other end of the spectrum you have Monte Carlo methods. In between you have eligibility traces. So eligibility traces are your link to go from temporal differences to Monte Carlo methods. Very interesting read, lots of pictures, which I really, really appreciated, very intuitive explanations. So there's lots of things that you can learn from this book about artificial intelligence and reinforcement learning, but specifically eligibility traces are like a very good place to go to, is this book for eligibility traces. And the second reference for today is something that Adlan's going to show you in the practical tutorials, the deep learning or the Google DeepMind research paper on asynchronous methods for a deep reinforcement learning. Yes, that's the paper. That's the one paper that the A3C paper that we're going to be discussing further down in this course. We're getting closer and closer to it. And as you can tell, we're pretty excited about this. So this is going to be looking a little bit at how they implemented eligibility traces in this paper. So we're going to be using this more for the practical side of things. So hopefully you enjoyed today's tutorial, and now you're a bit more comfortable with eligibility traces. And I can't wait to see you next time. Until then, enjoy AI.